to see my screen?
Yes.
Okay. Okay then. So we'll go ahead with our discussion. So till now we have seen three-phase system, star connected and delta connected system, and we have seen some problems based on that. Okay. So please switch off your mics. Okay. So we'll see what are the instruments that is used to measure power and how we are going to measure power in single phase and three phase circuits. Okay. Right. So basically, which instrument is used to measure power? Hello. Which instrument? Yeah.
Voltmeter.
So wattmeter is basically used to measure power. So it will measure the active power in your circuit. Okay. So if you see the basic, construction or what are the different parts that are present in a wattmeter, you can see here, right? It contains two separate coils. Okay. So one of these is called as current coil. Okay, and made up of heavy wire. Heavy wire means since it has to carry current, right? So it will basically carry the load current. Okay, so that means it will have the area of cross section of this current coil will be should be sufficient to carry that load current. Okay, they will design in such a fashion. Okay, and it will have low resistance and is connected in series with the load, right? So since it is connected in series with the load, so it has to carry the load current, right? So that's why it should be designed such a way that based on the load, its cross-sectional area or its current carrying capacity needs to be designed. Okay, and obviously it should have low resistance because if resistance is there, that will also consume some amount of power, and your calculation of actual power measurement will get affected. Okay, so it will have low resistance and it is connected in series with load, and right, and it is basically a heavy wire. Okay, so next, if you see, there will be one more coil, which is second coil, which is called as a potential coil or a voltage coil. Okay, this coil, if you see here, composed of much greater number of turns of fine wire with relatively higher resistance, right? So what it means, its potential coil will have fine wire. Fine wire means thin wire. Okay, because here the objective is not to carry the load current. Okay, it has to measure the voltage. Okay, right. So it will have very fine wire. That means not much current carrying capability. So to reduce the current flowing through it, you will have a resistance, right, connected in that, and it is connected in parallel to the load, right? If you see here in the circuit, one thick wire is there here. If you see, this is connected in this fashion, and it is coming here. So it is connected. This coil is actually connected in series, right? This center coil, which is written as potential coil, it is actually connected in parallel to the load, and the other one is actually connected to load in series, right? So this coil and this vertically big one, which are shown on the screen, are basically called as current coils. So that are connected in series with load, and the potential coil is actually connected in parallel with the load with some resistance in connected in the circuit. Clear? So potential coil is connected in parallel to the load, and current coil is actually connected in series with the load, right? So, and there is one more called as pointer. If you see any instrument, if you want to read, it should show some deflection, right? So that means some needle will be moving, which will give you the indication of the reading. Okay. So that needle is also connected to the potential coil, right? Okay, so coming to basic construction, it consists of two coils. One is current coil, another one is potential coil. Potential coil is connected in parallel to the load. Current coil is connected in series with the load. Okay, and the pointer is connected to potential coil. Okay, so both the voltage and current coils will produce magnetic fields, obviously, right? When current is flowing, it has to produce magnetic field. So magnetic fields are produced. These fields will interact with each other and produce a deflecting torque on the voltage coil. Okay, so that means these current coils are fixed. Okay, they are actually fixed to the frame or body of your instrument. Okay, of your meter, wattmeter. But this potential coil is not fixed. That means it will be balancing on some small point. Okay, so whenever these two magnetic fields interact each other, obviously there will be a deflecting force acting on the potential coil. It is of lightweight potential coil, right? So obviously when it deflects, it will give you some indication or some reading on your meter, which you can understand that it is some power it is showing. Okay, so basically the interaction of the two magnetic fields will result in a force on the potential coil, which will be showing you some reading. Okay, so the torque applied on the moving system, here the moving system means voltage coil and the pointer, okay, is proportional to the instantaneous product of the currents flowing in the two coils. Okay, that means obviously it should depend on the current flowing on the two coils. Okay, that's why some force is acting on the potential coil, right? The deflection caused is proportional to the average value of the torque. Okay, right. So it will give you some average value of torque. So that will be seen as reading on your screen. Okay. So it will be calibrated such a way that it will the deflection will be proportional to the wattmeter reading, which was displayed on your screen. Okay. Is it clear? So this is the basic construction. So basically it operates on the force which was caused because of the interaction of two magnetic fields. One magnetic field is proportional to the voltage and another one which is proportional to the current. Okay, so that's how we are going to get some deflection, and that deflection is calibrated and made it in terms of watts at the output display. Is it clear?
Sir, why the current coil made of heavy wire?
See, heavy wire means thick wire. The meaning of heavy wire means thick wire. Okay.
Area
Thick wire, why it is
cross-section
required
higher.
means, I mean, you understood or anything else? The meaning of thick wire means when you are designing a current coil, it is actually going to be connected in series with the load. Okay. So let's say my load is going to, when I install something, I will know what is my load current, right? So load current is 100 amperes. I will try to make that the current coil is something it can carry 120 amperes or 130 amperes. Okay. So that's the meaning of thick wire or heavy wire. Okay. But potential coil, we don't want more current to flow through the potential coil, because if it flows, obviously some losses will take place. If some losses are taking place, your wattmeter itself is consuming some amount of power. Okay. So your actual power consumed will be, I mean, not accurate. Okay. So with that intention, they will place a resistor in the potential coil. Intentionally they will place, so that the current flowing through this potential coil will be reduced. So the error in your reading will be less. Okay. So that's why. So since the current flowing in this potential coil is less, so a small or thin wire is sufficient enough to carry that current. Is it clear?
Yes, sir.
Sir,
Yeah.
sir, what is pointer is made of, sir?
Pointer, pointer is nothing but a needle. How you see in the in mobile, how you will see, not in mobile, in watch will be some needle will be there, right?
Yes, sir.
So some kind of needle they will use, and mostly it will be a non-magnetic material, or it will not generate some flux. Okay.
Okay, so okay, sir.
So they should make sure that some flux interaction will not create some error in that needle. Okay. Right. So point is basically like watch how you will see in a similar to that. It's basically a needle, that's all. Thin needle with of lightweight. Okay. So this is the basic construction and operation of your wattmeter. Okay. So let's see. Okay. So you have seen the basic wattmeter construction. That means it will have two coils. So how to connect this wattmeter in your circuit? Okay. Right. So the wattmeter is used by connecting it into a network in such a way that the current flowing in the current coil is the current flowing into the network, and the voltage across the potential coil is the voltage across the two terminals of the network. Okay. So what it says is, let's say this is the passive network. Okay. And you want to measure how much power is flowing into this passive network. Okay. So wattmeter will give you 4 terminals. Okay. So obviously current coil will have 2 terminals and potential coil will have 2 terminals. So these 4 terminals you have to connect in your passive network. Okay. So how they will do? Current coil should be connected in series with the network right there. This is your passive network. So series means it should be connected in this fashion. Okay. And potential coil should be in parallel with your load. Okay. So it will be connected in this fashion. Okay. In shunt format. Right. So this is how you have to connect. Okay. I have got power. So that's good news. Wait. 1 second. Okay, you are able to hear me?
Yes, sir.
Okay. So you are able to hear me and you are able to see me also, right? Okay, then fine. Okay, so we have 2 coils in the wattmeter and these should be connected to your passive network. So this is how you have to connect. You will have current coil in series with the load and potential coil in parallel with the load. Okay. Next is when you have 2 terminals, okay, some indication should be there. Okay, so let's say you have terminal 1 and terminal 2 for current coil and terminal 1 and terminal 2 for current coil, for potential coil. So whether I should join one, so there is some common point now. If you see here, this is a common point. That means the second terminal of the current coil is getting connected to first terminal of your potential coil. Okay, right. So there should be a common point for both the coils. Okay. So there are wattmeters of are different makes. That means the second terminal and the first terminal of the potential coil will be connected, or the first terminal of the current coil will be connected to first terminal of the potential coil also. Okay, both are possible. In the olden days, olden days means 10 years back, they used to have this kind of connection. Okay, That means the second terminal of the current coil is the same as the first terminal of your potential coil, as shown on your screen now. Okay, right. So what it means is each coil has two terminals, and the proper relationship between the sense of the current and voltage must be observed. Okay, right. So each coil has a positive marked terminal. Okay, so as you can see here, both coils are given with some positive marked terminal. Okay, an upscale reading is obtained if a positive current is flowing into the positive end of the current coil, while the positive terminal of the potential coil is positive with respect to unmarked end. So what it means is you should connect such a way that the positive marked terminal current should enter for the current coil, and the positive marked terminal for the potential coil should be at a higher potential compared to unmarked terminal of your potential coil. Is it clear? So it should be connected as shown on your in the circuit as of now. You're understanding now? So here this is the positive terminal, current is entering into the positive terminal. Here for the potential coil, this is your positive terminal, and this is at a higher potential compared to other terminal of your potential coil. If you connect in this fashion only, some positive current will be flowing into your network, and there will be a deflection seen on your wattmeter. Understood? So that means power is getting consumed by your passive network if you are connecting in this fashion. Then only wattmeter understands that some positive power is there, and it will give you deflection. Is it clear?
Sir,
Yeah. Any doubt on this, or is it clear to you?
Sir, which one is at lower potential, sir, in potential coil?
So this is your potential coil, and this top one, that means this point is your positive terminal. Okay. And this is your negative terminal, because they have given plus here now. So this plus corresponds to this terminal. Okay.
Yes.
So to show some reading on your screen, on your wattmeter, to show some deflection, that means needle will indicate some power only when current is flowing into the positive terminal of your current coil, and voltage at the positive terminal of your potential coil is higher compared to unmarked terminal of your potential coil. Okay. So that means voltage should be positive, and current also should flow into the positive terminal of your current coil. Then only some positive power is flowing into your passive network, and it will give you some deflection. Okay. Is it clear?
Sir,
yes.
current after entering the current coil, how it flows, sir?
After entering to?
After entering and leaving the current coil, how the current flows, sir?
It's a series circuit, na? Right. So after coming from the current coil, it has two parts. One is potential coil. It can flow through potential coil, it can flow through your passive network. But the current which will flow through your potential coil will be very negligible. Why? Means they will have a large resistance in at this point. As you can see in the previous figure, here I am intentionally connecting a large resistance in the potential coil. The objective is I want to minimize the current flowing through this path. That's why I am connecting a large value of resistance. Okay, if I do that, so what will happen? The current will mostly take its path through this passive network only. Okay, right. So that's why we are connecting some resistance in that, so that the current flowing into this potential coil will be very small as compared to this one, as compared to current flowing into the passive. Let's say 100 amperes is flowing in this, maybe 0.5 or less than that will flow into this potential coil. They will design such a way that in such a way they will use large resistance. Is it clear? Why? Means because you are measuring power. If your wattmeter itself is consuming some amount of power, then your actual reading is not the accurate one. The reading what you are getting is not accurate. Okay, so they will design such a way that wattmeter power consumption will be very small, as minimum as possible. Okay, that's how they will design. Okay, is it clear?
Sir, for the diagram, the center one is
Potential coil.
voltage, sir. Voltage coil, sir.
Yeah, voltage coil or potential coil, both mean the same.
Okay. Okay.
Okay, right. So last point, what it says is reversal of either coil, but not both, will cause the meter to try to deflect downwards. That means if this is not happening, that means current is not entering into your positive terminal of your current coil, or your positive marked terminal is not at a higher potential compared to unmarked terminal of your potential coil, then your coil will try to deflect in the downward direction. You are creating a force in the opposite direction of your scale. You are understanding or not? Let's say you have a current coil and you have a potential coil. Initially, when no supply was given, your needle is at 0. That means water reading is 0. Now, I should create a force proportional to the power consumption such that the needle will move in, let's say, in clockwise direction, and it will show you some deflection. Okay, but if you are not connecting properly, so the force will be created in the anti-clockwise direction, and already it is at 0 potential, and there is no space for your needle to move in the anti-clockwise direction because the lowest reading or the lowest position is 0 itself. You are understanding? So the force should be created on the needle in such a direction that it will move in the clockwise direction, and it will show you the power proportional to the consumed power in the network. Okay, if you are creating a force in the opposite direction, then needle can't move because that is the minimum it can be there. Okay, so it will remain at 0 itself. Okay, you are understanding? So what I am trying to say is, if you are not connecting your terminals in the figure shown here, then there will not be any deflection even though there is power consumption in your circuit, because your force is in the opposite direction and your scale is on the other way. Yeah, I hope you understand. Is it clear? So can we go ahead? Okay then. So this is how you have to connect. So for your better understanding, I have given you some circuit and I have given you the wattmeter connections also, right? So let's say you are able to hear me, right?
Yes, sir.
Okay. So let's say you have a passive network which consists of two sources and some passive elements. Okay. So you have left-hand side source V1, some value is there, and your objective is to find out the power consumed or power flowing into your right-hand side source, that is V2. Okay. So how to connect? You have wattmeter is given to you, and the 4 terminals are available with you. Okay. Okay. So this is your positive terminal for the current coil, and this is your positive terminal for the potential coil. Okay. So now these wattmeter, instead of saying always positive and negative, positive and positive terminal, they have given some labeling of names. Okay. So those names are denoted as M, L, C, and V. Okay. So this is the terminology they have adopted for your wattmeter. So when you see a physical wattmeter, these 4 terminals will be available to you for your connection. Okay. So at M, you have to bring some wire from your circuit and connect at that point. Okay. Can anyone guess what could be the, full form of this M? M stands for what? Or anything, M, L, C, and V. Can anyone guess? At least V you should be able to guess. Okay. So M stands for here main. Okay. M stands for main. So it is coming. It is connected to main. So that's why it is called as main. Okay. Right. And L stands for line. Okay. And C stands for common. Why common means this terminal is common to both your current coil and the potential coil. That's why they will call it as common. Okay. And V stands for voltage. Is it clear? So V stands for voltage means because it is related to potential coil, that's why our voltage coil they call it as V. And C stands for common because it is common for both current coil and the potential coil, the terminal. And L is in line with your wherever you want to measure power, it is in line with that. So that's why they call it as line, and M is the main which is coming from the other side. Okay, so they call it as M, L, C, and V. Okay, right. Is it clear? Sometimes this C can be on this point also. Okay, so previously they used to use this connection. That means L and C are joined. Now latest wattmeters, what they are doing is M and C they are going to join. That means this terminal will be on at this point. That's all. Okay, so this is how you have to connect the 4 terminals available on your wattmeter into your circuit such that some power will be shown on your wattmeter screen. Okay. So connection is made such a way that an upscale reading corresponds to a positive power absorbed by the right hand source. Okay. So if you connect in this fashion, then obviously some power will be absorbed by this. If power is absorbed by this source, then some deflection will be seen on your wattmeter. Okay. So what is the basic formula for power? So V2 magnitude, V2 RMS into I RMS into cos of angle of V2 minus angle of I. Okay. Right. So this is the basic formula. So accordingly, it will show you the reflection. That means the power which you are calculating and the power which is shown on your wattmeter screen physically, both will be same. Is it clear?
Yes, sir.
Okay. So basically you have to remember that M, L, C and V terminals, and you have to connect accordingly in your circuit so that some power consumption, that proportional reading will be shown on your screen. Okay. Okay, let's see some. So that's what back here you have seen only a single phase circuit and how to connect a wattmeter in a single phase circuit so that power will be recorded. Okay. So how to measure power in a 3-phase circuit? Okay. So 3-phase circuit will have 3 lines. Okay. So how to connect wattmeters? Whether one wattmeter is sufficient, or you require 3 wattmeters, or you require 2 wattmeters to measure power in a 3-phase circuit. Okay. So you can use 3 wattmeters and measure power in all the 3 phases and simply add up all those 3. That will give you the 3-phase power in a circuit. Okay. There is one more method by which using only 2 wattmeters also you can measure power in a 3-phase circuit. Okay. So that we are going to see now. Okay. Using 3 wattmeters is pretty simple. Simply connect 3 wattmeters in the 3 phases and add up all those 3 values. That's all. That will give you the power. But using 2 wattmeters, how to measure the power? That we will see. Okay. So 2 wattmeter method. In measurement of power using 2 wattmeters, the sum of the readings indicate the total power. Okay. Regardless of load is balanced, load is unbalanced, source is unbalanced, and difference in the 2 wattmeter readings. That means in a 2 wattmeter method, we are going to use only 2 wattmeters to measure the total power. Okay. Whether the load is balanced or unbalanced, it is immaterial to us. Whether the source is balanced or unbalanced, it is immaterial to us. Okay. Whether the 2 wattmeter readings is same or different, also not an issue. Simply add the two wattmeter readings, that will give you the total power consumed by the three-phase load. Okay, right. So that's what it states. So using two wattmeters itself, you can measure the power consumed by the three-phase load. Okay. So now the question comes, how to connect those two wattmeters in your circuit, right? Because you are having two wattmeters and three lines are there with you. So how to connect that? So that we are going to see now. If we assume the wattmeter corrections are sufficiently small so that we can ignore them. So that means if we assume that there is no power consumed by the wattmeter, that means we are assuming an ideal wattmeter, or the power consumed by the wattmeter is very much small and it can be neglected. Okay, so that is the assumption we are taking, right? So wattmeter 1. So current coil is in line A. So you have to connect in this fashion. So in line A, we are having a current coil. Okay, and the potential coil is between lines A and B. So this is your A terminal and this is your B terminal, and potential coil is connected. Okay, here in this fashion. Okay. So that means the voltage across the potential coil is basically VAB. Okay, and the current flowing into the current coil is basically IAA, right? Because it's a line current, so IAA. Coming to wattmeter 2, it will also have two coils, one is current coil and the one is potential coil. So the current coil is in line C. So that means I have connected the current coil in line C, and the potential coil is between lines C and B. So between C and B, I am going to connect the potential coil. That means the B phase, we have made it common terminal for both the wattmeters. Okay, right. So line B is considered as a common point of connection for both the wattmeters. That means for both potential coils are connected to this common point. So if you connect in this fashion, then the reading of wattmeter W1 or P1 and the reading of wattmeter W2, if you add up, that will give you the total power consumed by this load. Okay. So what will be the reading of wattmeter W1? It will be by the same basic expression which we have already seen. Right. So what will be the voltage here? For wattmeter W1 reading, what will be the voltage?
VAB.
What will be the voltage?
VAB.
The basic formula is Vrms into Irms into cos of angle difference between the voltage and current you are considering. Okay. So what is the voltage applied to your potential coil of wattmeter 1? Since the potential coil is connected between line A and line B, so the voltage VAB RMS value you have to consider when you are calculating. Okay, so VAB magnitude, there is RMS value. And what is the current flowing? IAA. So RMS value of the current IAA into cos of angle between VAB minus angle of IAA. Right. So this you already know, right? So Vrms into RMS into cos of theta minus phi. So that's what is basically this formula is.
Sir, sir, how this current will be flow in what?
Can you say it louder, please?
Sorry, sir.
Can you say it loudly?
Sir, I want to ask that how IAA. IAA, sir.
IAA is the current flowing through your current coil. See, when wattmeter will give you some deflection, on what principle it is working? It is working on the principle of magnetic forces. That means the magnetic fields created by current coil and the potential coil. Okay. So this is one magnetic field. Current coil is creating one magnetic field and potential coil is creating another magnetic field. Okay. Right. The interaction of these two will give you a deflection on your needle. Okay, right. So the current flowing in the current coil is what is creating the field. Okay, so that field will be proportional to the current flowing in it. Na? So that is nothing but IAA. You're understanding? The field produced by this fellow current coil is proportional to IAA because the current is flowing through that coil. Okay. Similarly, the field produced by the potential coil will be proportional to the current flowing in this potential coil. Okay. How? This voltage divided by that resistance, how much they are having. They have right. So that's why it is proportional to voltage VAB. Is it clear?
Sir, we want to calculate power 1, sir. P1.
Yeah.
P1 equal to VRMS into IRMS into cos of theta minus phi. And sir,
Yes.
And sir, power in this, the I is current flowing through the positive terminal. But in this, sir, where the PC is written, we want to calculate only the current in PC, sir, not IA, sir.
No, you are talking about single phase circuit. Maybe you are thinking this is I can connect in this fashion now. So what is happening here is wattmeter has 4 terminals, okay, and one current coil and one potential coil is there. If I use 3 wattmeter method, okay, so as you are saying now, in 3 wattmeter method what will happen is one neutral terminal will be there, okay, so each phase will have 1 wattmeter, okay, so current flowing in the current coil of wattmeter 1 is nothing but your line current or phase current, whatever maybe star connected system, both are same, and the voltage across wattmeter 1 will be phase voltage VAN, okay, in 3 wattmeter method, because in that 3 wattmeter method you will consider neutral as your reference and potential coil of wattmeter 1 will be connected between A and neutral. Potential coil of wattmeter 2 will be connected between B and neutral. Potential of coil of wattmeter 3 will be connected between C and neutral. Okay. So in that scenario, you require 3 wattmeters, and straight away the wattmeter 1 reading is nothing but the power consumed by phase A load. Power consumed by phase B load is given by wattmeter W2. Power consumed by phase C load is given by wattmeter W3. So that is the case when you are using 3 wattmeters in your circuit. But this is a scenario where by using 2 wattmeters itself, I am trying to calculate the total power. That means I am trying to, reduce my number of wattmeters required, and I am reaching my objective of measuring the power. Okay. So in that case, you can't connect in that fashion because you are always with only 2 wattmeters. So this is the method they are adopting, and you will observe that reading of W1 plus W2 will be same as the total phase power consumed by the load. Okay. So that is the reason why you are connecting between 2 lines, A and B, the potential coil, and current is flowing in one current coil which is proportional to one line current. Okay. So this is a different method where using 2 wattmeters I am trying to measure 3 phase power. So using this method, I am able to calculate the total power also. Right. You will understand once you see the one problem. Okay. So in this circuit, you have to connect in this fashion, and since the voltage applied across the potential coil is VAB, so you have to consider VAB RMS value into IAA RMS value into cos of angle between difference between those two. Did you get some idea?
Yes, sir.
Yes. Okay. So what you are talking is 3 wattmeter method. In that case, your voltage is phase voltage and current is your line current or phase current, star connected system. But using 2 wattmeters, it's a different. Simply I'm changing the connections. by changing the connections in such a way that you will understand that at the end I will get the total power. Okay. So this is how you have to connect. That means potential coil will be connected between any two lines and current coil will be connected in one of the lines for one wattmeter. Similarly for the other wattmeter also. Okay. That means one line is going to be a common terminal for both the potential coils of the two wattmeters. Okay. If you see P2, same thing. The voltage applied is this is your positive terminal. So CB you have to consider. So that's why VCB. And current flowing is ICC. Okay. And cos of angle between difference between these two. Right. So if you connect in this fashion, let's say this fellow is giving a reading of P2. P2 means some value it is giving. P1 is also giving some value. So if you simply add up those two, algebraic addition, that means taking sign into consideration. Okay. Then the total power in balanced or unbalanced load will be nothing but addition of these two. Okay. So total three-phase power is P1 plus P2, reading of 1 wattmeter and added to reading of other wattmeter. Right. So this is how you can measure a three-phase power in a three-phase circuit using only 2 wattmeters. Okay. Right. So let's check whether it is. Let's check that for some circuit. Right. So power measurement in a three-phase balanced load. So I am considering a balanced load, okay, in a delta connected fashion, as you can see here. Okay. In the case of a balanced load, the 2 wattmeter methods enables the power factor angle to be also be determined along with the total power. That means if your load is balanced, along with the power measurement, you can also measure the power factor of the load also by simply with the readings of the 2 wattmeters. We'll see how is it possible. Okay, so assume a balanced load impedance with a phase angle of theta, either a star or delta connected system. Okay, that means what we are going to see is applicable for star connected system as well as for delta connected system. I have considered a delta connected system, delta connected load, and I am trying to check whether I can find power factor or not. What will be the formula for that? Okay, so let's see that. Okay, so you can see here there are 2 wattmeters. One is connected in phase A, another one is connected in phase B and phase C, and B is common terminal. So can you write the expression for the reading of wattmeter W1? What will be the expression for reading of wattmeter W1?
VA1 mod VA1 into mod IA into cos of angle VA AB angle IA.
Okay, right. So it is VAB into IAA into cos of angle between those two. Okay, right. If it's a balanced system, VAB is basically a line voltage. So can I represent this one with VL? Right now, since it's a balanced system, all the RMS values of voltages, okay, between AB, BC and CA is called as line voltage. Okay, so I can represent that with VL. Okay, and I can represent the current flowing in the line with IL. So IL indicates the line current. Okay, right. So what you have told, that is the first expression. Okay, and that is VAB into IAA into cos of angle difference between those two. Right. So if I consider this is as my phasor diagram. So for this circuit, what is shown here, the phasor diagram will be this one. So try to understand this phasor diagram. Let's see that. Okay. So I am taking VAB as my reference phasor. Okay. So what is the voltage applied across these two terminals? Voltage across these two phase terminals.
VAB.
VAB. So VAB is the voltage applied to this impedance ZP at an angle of theta. Okay. Right. So what will be the current? VAB divided by ZP at an angle of theta. Right. This expression what is shown here. So that means your current will have a phase angle lag of theta degrees with respect to VAB. Correct na?
Yes,
Yes,
sir.
sir.
Yeah. So current is going to lag with respect to your phase voltage. Delta connected system phase voltage and line voltage is same, right? So current is going to lag by this angle theta. Okay. Similarly for other phases also. This is VBC and IBC is going to lag VBC by an angle of theta. Similarly for VCA. Okay. Right. Now we have to find out the phase angle difference between VAB and IAA. So where will IAA fall? This is your IAB. This is your VAB. Now you have to find out IAA. Okay. So what is the formula for IAA? If you see from the circuit, IAA is equals to IAB minus ICA. Correct. Applying KCL at this node here. IAB minus ICA. So ICA is here. Opposite minus ICA will be at this point. Okay. So you have to add up these two phasors. That means IAB and minus ICA. If you add up, you are going to get IAA. Okay. Right. So since it's a balanced network, these two are of same amplitude. Obviously, your IAA will be coming exactly at the middle of these two phasors. So it will have a 30 degrees with respect to this film. So what is the phase angle between VAB and IAA? Phase angle difference between VAB and IAA.
Plus 30.
Theta plus 30.
30.
Okay, theta is coming from your impedance value ZP and 30 is coming because you are adding up these two phasors. So the total phase difference is theta plus 30 degrees. So that means P1 reading will be, reading of this wattmeter will be corresponding to this value what is seen here. VL into IL into cos of theta minus theta plus 30 degrees. This will be the reading of wattmeter W1. Okay, so theoretically if you calculate using this and practically you connect your wattmeter in your circuit and check, both values will match. Okay, so what will be the formula for reading of wattmeter W2? It is connected in phase C, so you should have ICC and it is connected between C and B because plus terminal is at C. So between C and B it is connected. So VCB into ICC into cos of angle difference between those two, right? So what will be the phase angle difference between VCB and ICC? Same thing you have to apply here. Your VCB, where is VCB? Here, right? And ICC, where it is going to fall? ICC is equals to ICA minus IBC. So ICA is here minus IBC. That means it will come in this direction, right? So you have to add up this ICA and minus IBC. So it will come exactly at this point. Okay. And the phase angle difference between VCB and ICC will be 30 minus theta. Is it clear with regards to this phasor diagram and how I have got the phase angle? Or any doubt in this phasor diagram?
Sir, how are IAA?
What?
IAA.
I
AA at an angle of 30.
See, this is,
Sir,
you got it or not?
no, sir. IA, no, sir.
You are talking about power P2. Okay.
Sir, IAA.
IAA.
Yes, sir.
Okay. So
30
see
degrees.
here, this is your voltage, and current IAB will be lagging this voltage by an angle of theta, because theta is coming from your impedance, whatever you are
Yes.
connecting to the network. So IAB you have got. In this formula, you have to find out the phase angle difference between VAB and IAA, because IAA is the current flowing in the current coil of your rod. So IAA. So IAA, if you see, this is the current coming into your node terminal A. So if you are applying KCL at this point, at A, IAA is equals to IAB minus ICA. Correct now? IAB minus ICA. IAB is flowing from here to here. ICA is coming into that. Right. So simply apply KCL at this node here. IAB you already know. ICA I have to find out. Okay. ICA is here. Right. But according to the equation, IAA is equals to IAB minus ICA. So minus ICA, where it will fall? Exactly opposite to this phasor, it will fall here. Okay. Now you apply parallelogram law of addition of these two phasors, IAB and minus ICA. If you add up, you are going to get, what is the phase angle between these two? It will be 60 degrees, and your resultant phasor will be exactly 30 degrees. Correct na?
Yes, sir.
Okay. So our objective is to find out phase angle between VAB and IAA. Okay. So this 30 is coming because of the phasor addition of these two phasor currents, and theta is already existing between these two. So total will be 30 plus theta. So that's what is written here. You got it?
Yes, sir.
Okay. Similarly, if you think, you will get theta 30 minus theta degrees for the second wattmeter also. You have to simply see what is the voltage and what is the current. Accordingly, you have to draw the phasor diagram. So you will get P2 is equals to VLIL into cos of 30 minus theta. Okay. So this is how even for a star connected system also you can apply. For we have considered a delta connected system, and for this, so this is what you are going to get: wattmeter reading W1 and wattmeter reading W2. You have to draw the phasor diagram and then find out the phase angle between the corresponding lines and currents. Okay. Right. So this is regarding 2 wattmeter method, how to connect the 2 wattmeters in your 3-phase circuit, and whether the load is balanced or unbalanced, you will get the total power by the 3-phase load, which is simply P1 plus P2. If it is a balanced load, you can also find out the power factor of the load, right? So in the previous slide, you have seen P1 and P2 expressions. For the considered balanced delta connected load, the power factor can be found using P1 and P2. Okay. So simply try to calculate P1 divided by P2. Here, you try to calculate P1 divided by P2. You are understanding, na? I have given you P1 expression, I have given you P2 expression. Try to calculate P1 divided by P2. You will get in some terms of cos theta plus 30 divided by cos theta minus 30 minus theta. So expand that cos function and try to do that.
Sir,
Yeah.
cos theta plus sin theta.
Okay, you expand that cos function and substitute that cos 30 and try to calculate that. P1 by P2 you do expand that cost function, and if something is there, you can cancel it.
So
So
root
that
3
means,
cos theta minus sin theta upon root 3 cos theta plus sin theta.
okay, can you convert that in terms of tan function something?
Yes.
Okay. So try to do that. P1 divided by P2 is cos 30 plus theta by 30 minus theta. So if you expand that is this cos function and try to multiply everything, if you solve it, you are going to get tan theta is equals to root 3 into P2 minus P1 by P2 plus P1. Did anyone got this? Someone has got this answer or not? Okay, so it's nothing but simply you have to expand that cost function, and if something is common, cos 30 you substitute and try to cancel whatever is possible and try to solve it. So you are going to get tan theta is equals to root 3 into P2 minus P1 divided by P2 plus P1. So that means if the load is balanced, okay, you can find out the power factor angle also, okay, by seeing the readings of your wattmeter. Okay, so difference of the two wattmeter readings divided by sum of the two wattmeter readings multiplied with root 3, that will give you tan theta, and from that obviously you can find out theta and you can get the power factor cos theta also. Okay, is it clear or anyone has doubt in this?
No, sir.
Okay, so you should get this expression. It's simple mathematics, you will be able to solve it. Okay, right, so I have told P1 plus P2 will give you the total three-phase power consumed by the load, right? So you have the expression for P1, you have the expression for P2. Try to add up those two. The total real power drawn by the load is sum of the two wattmeter readings. Try to add P1 plus P2. That means VL-IL into cos of 30 plus theta plus VL-IL into cos of 30 minus theta. So VL-IL will be common. Okay.
Root 3 times VLIL into cos theta.
Into root 3 time cos theta.
We'll repeat it one more time.
Root 3 VL IL cos theta.
Root 3 VL-IL cos theta. Others also please try to do that.
Yes, sir. Root 3 VLIL cos theta, sir.
So root 3 VL-IL cos theta. Okay. So if you remember in the last class, we have discussed what is the total power. Okay. It is root 3 VL-IL into cos theta. This is the total three-phase power. Right. So that means from the readings of the two wattmeters, if it's the load is balanced, you can find out the power factor angle, and whether the load is balanced or unbalanced, whether the source is balanced or unbalanced, whatever it may be, the total power P3 phase is simply P1 plus P2. And if you solve it or if you expand it, we have already seen or we have already proved that P1 plus P2 reading will be equal to your three-phase power. If you remember, this is the three-phase power, total three-phase power we have already discussed in the previous class. Root 3 VLIL into cos theta. Correct now? So that means mathematical also we are going to prove that we have proved that the total power reading P1 plus P2 is equal to your three-phase power. Is it clear? Or any doubt in this? Okay, so that's it for today. So we have seen how to measure, how to connect a wattmeter in a single phase circuit and measure power. We have seen the 2 wattmeter method, which is used to measure power in a 3-phase circuit in material of whether load is balanced or not, and the total power observed to be P1 plus P2. And if the load is balanced circuit. Then you can find out the power factor also, which is given by this expression √3 P2 minus P1 by P2 plus P1. Okay. Right. So that's it for today. We will meet again on Friday, and next week, mostly Monday, you will have an exam. Okay. Right. You will have an exam for 30 marks on single phase circuits only, not on 3-phase circuits.
Okay,
You are
sir.
understanding? Okay. Single phase AC circuits. That means chapter 2, not chapter 3. Okay. This letter and other things we are not going to have exam. Monday you will have exam on single phase AC circuits, mostly on Monday. Okay. Right. So I have already sent the tutorial sheet already to you. Try to practice that. Okay. So you will have 30 marks exam on Monday. I will send a mail accordingly. Okay. Today or tomorrow. Right. So please prepare well, and we'll meet tomorrow afternoon. Okay then.
Sir,
Yeah.
sir, I'm Pranjal. I haven't received my previous test marks.
Okay. You did not receive. Anyone else who has not received?
Sir, there were 2-3 more
Sir, I am also not
students.
Okay. So can you, send me mail? But yeah, I have to know your roll number. That's all. If I know roll number, I can send it to you.
Yes, sir. Yes, sir.
So whoever has not received, please send me mail. So I'll check your roll number, and accordingly how much you got, I'll reply to you. Okay.
Okay, sir. Thank you, sir.
Okay. Please prepare for Monday properly, because it's going to be a 30 marks exam, and 30 marks is more valuable, right? So that will be, if you perform well, that will be good for your grading. Okay. So we'll meet tomorrow afternoon 3 o'clock. Thank you, all of you.